All right, so the fundamental counting principle is what we learned yesterday, and basically it says, oh, thank you. Basically what the fundamental counting principle says is that if you have a job or a task or something that you want to get done, and that job or task or thing that you want to get done has multiple stages to it, different things that need to happen, then if you multiply the number of ways that each of those things can happen, you're going to get the number of ways that the whole job can happen. So I don't know anybody that calls them slacks anymore. Obviously, this is a little dated, but if Bill has 3 sweaters and 4 pairs of slacks, and he's going to put on a pair of slacks and a sweater, then there are 12 different outfits that he can arrange there to wear. And that's basically it. That's the fundamental of it, fundamental counting principle. But the questions, of course, get more complicated. So does anybody have any questions? I'm just going to say from the first set to begin with. Go ahead, Grace. 11C. So in question 11, we have license plates, and in C, we need to have 3 consecutive letters like ABC or BCD or CDE, right? And 3 consecutive numbers. So the first thing is with the consecutive numbers, I just want to close something out here. The first thing is, when you talk about the order of numbers, the order of the digits, you can either number the 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can go from 0 through 9 or from 1 to 0, 1 up to 9 and then 0. I like to think of the numbers or the digits as being this set of numbers. And then, of course, we have the alphabet, and I'm not going to write out the letters, all of the letters of the alphabet. We have A, B, C, D, E, U, V, W, X, Y, and Z, okay? If you want 3 consecutive letters, the first letter has to be a letter that has 2 more after it. So, for example, I can start with A. I can use A for the first letter because then I can put BC. I can put B because then I can put CD. But I cannot put either Y or Z, because if I put Y, the 3 consecutive letters that start with Y are Y, Z. We don't have anywhere else to go. And that means that there are only 24 letters you can choose for the starting letter. And by the way, as soon as you choose a particular letter for the starting letter, you've chosen the next 2 letters. So really, to think of this in the fundamental counting principle, it's really just which letter is the first of the 3. And there are only 24 options. And you must choose a starting digit. But it has to be a digit that will allow you to have that one and the 2 following it. So you cannot have an 8, and you cannot have a 9. Which means there are only 8 digits that you can choose for that starting digit. So if we multiply 24 by 8, we should get the answer. So okay, good. 192 probably. Yeah. Other questions from the first part only? Just, yep.
Question 4.
Okay, let's look at number 4. How many even 2-digit numbers can be made using these digits if repetitions are not allowed? So we want to make a 2-digit number, and repetitions for A are not allowed. So that means as soon as we fill up one of those blanks, we can't use whatever number went there in the next blank. Whereas if repetitions are allowed, we're allowed to do that. Now there is a restriction. These numbers have to be even, and numbers like 12 and 48 are even because they end in an even digit. So when we look at the even digits, there's a 2, a 4, a 6, and an 8. So this has to be a 2 or a 4 or a 6 or an 8. And this first digit has to be any other digit that wasn't used, right? So we do the restrictions first, and this is 4. Right? There's only 4 even digits. Now, of the 1, 2, 3, 4, 5, 6, 7, 8 numbers in the pool that we can choose from, we only have 7 remaining. So that means that we have to multiply 7 by 4 to get 28 for the answer there. The only difference here is that if we can repeat, this still needs to be even, which means there are 4 options, but we're going to have 8 options for the first one. And that means that this is 32. And sometimes on an exam, just so you know, you might be given this scenario and asked, how many more even 2-digit numbers are there if you can repeat than if you cannot? So you have to calculate this as being 32, this as being 28, and then getting 4 as an answer. Is that okay? Okay, other questions? Go ahead.
7.
Okay, let's look at number 7. There are 8 horses in a race. In how many ways can the first, second, and third place horses being selected? So this is often what happens is these questions seem very complicated, and you have all this information swimming around, but really what it boils down to is if I have 8 items, how many ways can I select from those 8 items that fit in these blanks? Now, there is something about the fact that it's a horse race that's important, and that's that you can't repeat. Repeating items in this particular case, let's say we have, Secretariat is a horse, and Lazy Mike is another horse. You can't put Lazy Mike in first place and put Lazy Mike in second place, right? You can't repeat. So the bottom line is the answer here is going to be 8 times 7 times 6. Which, by the way, is the same as the number of ways the horses can win the first place and first, second, and third place. Well, that's 42 times 8 is 350, I don't know.
336.
Okay. Is that okay? Other questions from the first section? Go ahead, Caden.
14A.
Okay, 14A. How many 3-digit numbers have digits that are all different? So again, we find a way to phrase the question so it seems like a different question, but all be different means you can't use the same digit again. You cannot repeat. And we want 3-digit numbers. You form numbers from the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's what we form the digits, the numbers from. So if we want a 3-digit number, the one restriction is that this cannot be a 0. Because if that is a 0, then it's not a 3-digit number, it's a 2-digit number. There are no other restrictions. There aren't. So we do the restrictions first and you put a 9 there. And then you say, well, how many can I choose from for the second blank? And again, I don't know that I really made this clear yesterday. I hope it's obvious. This 9 is not the number 9 that we've put there. It's 9 different choices. 9 different options to choose from. Now we go to the next blank. How many options are there for the second one? Well, because we can't repeat, there's only 9. I don't know which of these from here to here. I don't know which one went in the first blank, but one of them did. And that leaves 9 left in the pool. And then we're down to 8. Does that make sense? Yeah. So if we go 9 times 9 times 8, that would be the answer. If you go now to B or C, we would just extend it, right? If you look at B, this is what you would do for B. You would just have a fourth number, or a fourth digit rather. Last call for any questions from the first section. Jack? 10? 10? Sports club has 30 members and you want to pick a president, vice president, secretary, and treasurer. Assuming, and this makes perfect sense, I don't think many organizations would allow somebody to be the president and the vice president. Right? Assuming you have to have 4 different people, then how many different ways can the positions be filled? Well, it's the Bobby Bear idea, except that Bobby Bear isn't just selecting a pair of pants, and he isn't just selecting a shirt. He's selecting a president. Well, there's 30 choices that he would have, or they would have. You need to choose a vice president. There's 29 choices, because you've already chosen somebody for president. You can't choose the same person twice. You need to choose somebody for a secretary, which would be 28, and then a treasurer, I think that was it, yeah, 27. It doesn't matter which blank you choose to fill in first in our thought experiment, you're going to have those 4 numbers multiplied together. Is that okay, Jack?
Yeah.
Okay. Let's take a look now at the second section. Does anybody have any questions on the second section? Go ahead. 9D. 9D, okay. All right. These A, B, C, and D here, I think they're all disconnected from each other. They're just 4 different questions. How many different non-zero numerals are possible using some or all of the numerals 0, 1, 2, and 3 if digits cannot be repeated? Okay. So since we have no specification on how many digits the numerals have to have, what that means is we could have 1-digit numerals or 2-digit numerals or 3-digit numerals or 4-digit numerals. And I'm going or 4 because there are 4 digits in our pool. So or means add. This is a very useful idea in this unit. A 1-digit numeral means we only have 1 choice to make. A 2-digit numeral means we have 2 choices to make. What's the first digit? What's the second digit? A 3-digit numeral means we have 3 choices, and a 4-digit means, of course, we have 4 choices. There are only 3 choices for this blank because it has to be a non-zero numeral. And they're adding that in here because you could argue that 0 by itself is a numeral, but they're saying non-zero. When we go to the 2-digit numeral, we forget about anything we've done here because of the word or. We've done that. Okay, now let's look at what would happen if we had 2 digits instead, which means or. This would be a 3. By the way, let's fill this in. Do you see that all of those first blanks will be 3s? Okay. Because we only have, if you have a 4-digit numeral, it cannot start with a 0, because then it's a 3-digit numeral. So how many digits do we have to choose from for the second placeholder in the 2-digit numeral? The answer is 3. Because we had 4 to choose from, we've chosen one of the 3 non-zeros for the first digit, so one of those 4 is no longer available. And we can't repeat, so we have 3 left. For that same reason, this would be a 3, but this would be a 2. So the reason why it's not going 4, 3, 2, it's not doing that nice progression that's a factorial, is because we have one little restriction on the first place, that we exclude the 0. And this would be 3 times 3 times 2 times 1. Does that make sense? Okay. Now it's just a matter of crunching those numbers. You're going to have 3 plus 9 plus 18 plus 18. 3 plus 9 is 12 plus 18 is 30. I think 48. That's good, Annalie? Okay. Other questions? Go ahead, Danielle. 8? 10? Okay. And you know, I could try to anticipate every single question for exams, but this is one, unless you've seen it, you would think you know what to do when you get the wrong answer. How many different sums of money, or you might not even know what to do, how many different sums of money using at least one coin can be made from 2 pennies, 4 nickels, 2 quarters, and 5 loonies? Well, we have 2 pennies, 4 nickels, 2 quarters. I'm just going to put 100 here for 100 cents for the loonies. So I'll just double check. You have 2 pennies, 4 nickels, 2 quarters, and 5 loonies. The thing you need to understand is you can get any sum of money you want by grabbing any of those coins. I could grab a nickel and no pennies and no quarters, and I could grab all $5, right? So what you need to do to create a sum of money is you have 4 choices. You have to pick a number of pennies, okay? And we'll get to the number that you're going to pick from in a second. And you need to pick a number of nickels. I mean, I'm assuming you know a nickel is, I guess it doesn't really matter if you know what it is or not. It's 5 cents. A quarter, you have to choose a quarter, so this will be the number of different ways you can pick quarters, meaning the number of different quarters you could pick. And then this will be the number of loonies. Now, how many different numbers of pennies could you pick? It's actually 3, that's right. Because you can pick 1 penny or 2 pennies or no pennies. So this is 3. There are 4 nickels. So that means there are 5 choices for how many nickels you can pick. There are 2 quarters, which means you can pick none or 1 or 2. There are 5 loonies, which means you can pick any number from 0 through 5, which is 6. Unfortunately, when you multiply these, I think you get, is that 170? 270? But that is not the answer. And there's a little wrinkle to this, that you have to have a non-zero amount of money.
So plus 5?
No. Minus 1. Because in all 270 of these, one of those 270 options was no pennies, no nickels, no quarters, no dollars, which means one of them, if you were to write them all down on 270 different Post-it notes, one of them would have a total of 0, and we don't want that. So that's why the actual answer will be 270 minus 1, which is, I hope it's 269. Yeah. Other questions? Go ahead, Sasha. 4? Yeah. Is this 4? Okay. So you were asked to determine how many ways you can go from, but I have a feeling I have these in, A is the bottom one, right? We'll do A first. How many ways can you go from A to B? Sometimes you'll see questions worded this way, that this is your campsite, this is the snack bar, and this is the beach. And the question is, how many different, and those are trails, how many different ways can you go to the beach if you want to stop at the snack bar? Well, believe it or not, it's exactly the same idea as Bobby Bear getting dressed. Except instead of making a decision about which pair of pants to put on and a decision about which shirt to put on, you make a decision about which trail to take you from A to the middle and which trail to take you from the middle to B. And since there are only 5 paths, to go from your campsite to the snack bar, and there are 3 paths to go from the snack bar to the beach, the answer is 15. Now, I want to point something out to you, and I don't know why it is. I can't, it happens a lot. On an exam, I give you a diagram like this, and people write 4 here instead of 5. And I don't know if they don't see that middle line or they miscount. It's a really simple idea. If you see it on an exam, don't make that mistake. Is that okay for A? Okay. Now, this next one is more complicated because you actually have different options here, different sets of choices or decisions to make here. One of them is, do you go along the top or the bottom? And basically what I'm going to tell you is that you can go from A to B this way, or you can go from A to B this way, right? You have to go along the top or along the bottom. And there's something in this question that would probably be on an exam which would say you're not allowed to backtrack. I don't know if it says that or not. But you are not allowed to backtrack because then there's literally no end to the process. So this is A to B through the top or A to B through the bottom. And of course, or means plus. So we're going to do the same thing with A to B through the top that we did in part A of this question. We're going to say that there are 3 options to get to that midpoint. There are 3 options to finish the task. So there are 9 options from A to B along the top set of paths. Plus, because it's or, we do the same thing on the bottom. There are 3 options here, but there are only 2 options there. When you follow the green general path, you have to go from A to the midpoint and the midpoint to B, which is why we multiply. Right? That's why we're not adding the 3 and the 2. You don't go one of these or one of these. You have to do both. And that gives us 6, so the correct answer will be 15. Is that okay? Good. We'll run into a similar question to that just looks different over and over again. Other questions? Go ahead.
14.
Okay, let's look at 14. So Sandra is writing an exam. It consists of 2 parts, A and B. Part A consists of 3 questions. The student must do 2. So we're starting to get an idea of what the little pieces are. The student has to complete 2 questions in part A. These are part A questions. They have to do that. And there are 4 part B questions, and the student must do 2. And part A must be completed before part B. If that restriction wasn't there, well, it would become more complicated or easier depending on how you look at it. But basically, she has to do part A and part B in this order. If she had the option of doing part B completely, then part A, we would find an answer and double it. Okay? If she just had to do 2 from part A and 2 from part B, and who cares, she could dance around from A to B, it's a totally different question. Okay? But the bottom line is there are a total of 3 questions in part A. So the first one she completes, she has a choice of any of those 3. And the second one she completes, she's already done 1, so there's 2 remaining. And she must complete 2 from the 4 question set. There's 4 to choose from for the first one she decides to do, and there will be 3 to choose from for the second one. It seems as though there should be something missing here, but no, you're just going to go 3 times 2 times 4 times 3. By the way, just give me a second to think this through. I'm not even going to finish my thought. Does that answer your question? Okay. Other questions? Go ahead, Grace.
7.
Okay, let's look at number 7. How many, this is the challenge question, okay. And I do want to show this to you because you never know when you'll see this on diploma exam. I had a conversation in my physics class this morning that there's this absolute monster of a question we did. It's like, I've never seen anything that complicated on a diploma exam except for once. And the likelihood that you would see it on a diploma exam is thin, but it's still there. This is one that you might see. Let's imagine that you just set out to solve this problem. No repeating digits, so we have the digits 0 through 9 to choose from, but once we choose one, we can't choose it again. We want a 4-digit numeral, and we have these two restrictions. Not to 0, did I get them all today? I did. And that has to be one of those digits. And yesterday when we did this with an odd one, we discovered that depending on which of those two restrictions you tackled first, you could get to an answer. But if you chose the wrong one first, filling in the second blank was impossible. Okay? What we're going to discover here is it doesn't matter which one you choose first, you're going to have a conflict. For example, if I said, well, this is 9, right? How do I know what number of these are left? Because this number that went here, this 1 of 9, this isn't the number 9, it's 1 of 9, might be in this list. It could be a 2, 4, 6, or an 8, in which case I don't know. Okay? On the other hand, this is even worse. If I say 5, I've got a bigger problem here. The bigger problem is I don't know if I chose a 0 or not there. And if I chose a 0, then this would actually be 9. But if I didn't choose a 0 here, this would actually be 8. And the only way out of this is to do the following. The only way out of it is to find the number of even 4-digit numbers that do not end in a 0, and to find the number of even 4-digit numbers that do end in a 0 and add them together. There's no other way that I've ever discovered or seen where it works. So if you say, let's just do the even ones that end in a 0. Well, this is 1. And you've used the 0, which means this is 9. And then this is 8, and this is 7. We could figure that out. Let's find the number of even 4-digit numbers that end in either a 2, a 4, a 6, or an 8. This would be 4. Grace, what number of options would we have for the first blank here? It would be 8, because we've got one of these 4 out of the pool, and we also still have 0 in the pool, which we can't use. This would be 8. Because we were down to 8 at that point, and then we're down to 7. So you can do the arithmetic here. If you multiply and add, you'll get the right answer. And I can't wrap my head around any other way you could do it if it's an even one. Because you have that internal conflict. The end could be a 0, but the front is not allowed to be a 0. Any other questions before we get started today? All right. So we're looking at part 2 of the fundamental counting principle. Today we're going to officially learn about factorial notation and officially learn about something called a permutation. So those are the two topics. You already know about factorial notation, so I'm going to not really race through this, but it's pretty straightforward. If I said to you, how many different ways can I arrange 7 books on a shelf? That's the same as saying how many different ways can I arrange 7 people in a line. You have 7 options for the first location, then 6, 5, 4, 3, 2, 1 down the line. The number is decreasing because we're arranging the items. So you can't put this person in the first place and put the same person in the second place. And we learned yesterday that this is abbreviated as 7 factorial. And I would say that's a fairly given fact that you know now. The number of ways to arrange items in a line is that number factorial. But now we're going to make things, we're going to elevate things to a Math 30-1 level. What does n factorial mean? Well, 4 factorial means 4 times 3 times 2 times 1. 22 factorial means 22 times 21 times 20, etc. N factorial means you take n, whatever number that is, and you multiply it by 1 less than n, which is n minus 1, and you multiply that by 1 less even than that, which would be n minus 2, and you continue to do that until finally you get down to 3 times 2 times 1. And in this course, n must be a whole number. Okay? N can be 0. 0 factorial is defined, and we'll define it in a second. But in this course, you cannot take the factorial of non-whole numbers. Now, just in case some of you go on and learn about factorials in post-secondary math, if you try to take 1.5 factorial, it works. Don't try to figure out what that means. It has no logical meaning in this course. If you try to take 1.2 factorial, it doesn't work. There's something else going on with factorials that we are not going to delve into. And I mention that because sometimes people play around on their calculator and then they go, well, wait a minute, I can do 1.5 factorial. Don't worry about it. If you want to have a discussion with me about it later, we can talk about it, but it's not important. N must be a whole number. By the way, 0 factorial is 1. Okay? And I'll explain why in a bit. Okay? It has to be 1. So to begin with, I do understand that on your handout, B probably says 50 factorial over 40 factorial, and it's equal to 4,800, no, 2,400? Okay. So let me fix this. I changed the numbers to make them a little smaller. And did I say 2,400? 2,450? Okay. So we'll get to that in a second. So, you know, what is 5 factorial? What is 10 factorial? I just want to make sure officially that you know how to do this on your calculator. Yeah. Instead of 10? Okay. I think those are the only changes I made in this lesson, but if there are other changes, then please let me know. 5 factorial, by the way, how many of you know that 5 factorial is 120 without even using your calculator? You've seen it enough, right? Like you see 9 times 7 is 63. Unless 9 times 7 is the one that stumps you. With me, it was always 8 times 6 for some reason. I don't know why. This is 120. I think 7 factorial is 5040, but that number just popped into my head. Is that right? It's 5040. And you know how to find that on your calculator. You do it in the same way that I was finding these factorials, even though some of them don't exist, and at least one of them makes no sense. Okay? I would like you to figure out, I just want to give you a minute to ponder this. Why is 50 factorial over 48 factorial equal to 2450? In other words, is there a way I could figure out it's equal to 2450 without using my factorial key and without actually figuring out what 50 factorial is?
50 factorial is 50 times 49 times 48, and since 48 factorial is on the bottom, all the things cancel.
Right. This is going to be a very important idea in a second. 50 factorial is 50 times 49 times 48 times 47 times all the way down the line 3 times 2 times 1. But this, as Jack just said, is 48 factorial. In fact, there would be nothing wrong with you writing 50 times 49 times 48 factorial and just ending it there. And on the bottom, we have 48 factorial. And the thing I want to point out to you, I haven't talked about this yet. Factorial has factor in the word. A factorial is a factor. So you have a factor of 48 factorial on the top, a factor of 48 factorial on the bottom. They cancel. This whole thing is gone. You're left with 50 times 49, which I'm assuming is 2450. Okay? And before we go on, I just want to highlight for you, and it may be obvious or not, I'm sure it's obvious when I mention it to you, the smaller factorial is inside of the larger factorial and not the other way around. The 48 factorial is a factor of 50 factorial. So if I said to you, simplify this expression, we do not have numbers to work with. This is a Math 30-1 course. But I know that n minus 2 is smaller than n, right? Which means that n minus 2 factorial must be contained inside of n factorial. Now, to see what 50 factorial over 48 factorial does, we expanded the larger factorial until we saw the smaller factorial. And if I do that here, I'm going to take n and I'm going to expand it. Whoops. And I'm just going to stop here. Don't write this down, please. How many of you would just do this? Okay, I'm not going to do that. I'm not going to dive into that idea just yet. When you expand this, you're going to get the following. And I want you to see what's happening to all of these terms. They're decreasing by 1 each time. But then eventually, however big n is, eventually it's going to decrease down to the number 3, and then 2, and then 1. And you might argue or question, why do we need to do this? And why do we need to write 1? I suppose you don't need to, but I like it to be complete. And this is over n minus 2 factorial, which we don't expand because then you say that this is n minus 2 factorial, so that cancels with that, and we're left with n times n minus 1. So the answer is n times n minus 1, or n squared minus n. n plus 3 factorial over n factorial. Well, which of those is a bigger factorial? N plus 3 is bigger than n. So n plus 3 factorial contains the n factorial. And that means to see the n factorial inside of the n plus 3 factorial, we expand the n plus 3 factorial. And I realize that many of you can, how many of you just know that the answer is n plus 3 times n plus 2 times n plus 1? I mean, if you can, you see what's happening here. I'm just formally writing it down like you would on a written response. So I keep decreasing by 1. When I get to n plus 1, it's going to become n, then it's going to become n minus 1, then it's going to become n minus 2. How far you want to take this is up to you. I would argue that I think this is fine even on a written response. I think that communicates the idea fairly well. I don't think you need to actually say times 3 times 2 times 1. And that means that this, which is n factorial, cancels with all of this, and the answer then is n plus 3, n plus 2, n plus 1. And I don't think we want to waste is the wrong word. I don't think we want to spend class time foiling that out. You could, but I'll leave that to you if you want to or have to on an exam. Any questions with B? N factorial over n times n minus 1. This is different because the bottom is not a factorial. I'm just curious, how many of you see that this is n minus 2 factorial? It's harder to see. I can tell because there are fewer of you that see it than saw the earlier ones. Let's just expand the n factorial to see what we get. just to see if it tells us anything. Kind of like with logs. If you don't quite understand something, write it in a different way. Maybe you'll be enlightened. Maybe you'll see something that you didn't see before. The bottom is not a series of factorials, it's simply factors. And now you can see that you have a factor of n on the bottom and a factor of n on the top. They cancel. Factor of n minus 1 in the numerator and denominator, they cancel. And we're left with n minus 2 times n minus 3 times n minus 4 all the way down the line, which means we're left with n minus 2 factorial. And that would be the answer. It's less easy to see this than it was to see the other two. All right, any questions with C? More on factorials in a bit, but in the meantime, let's talk about what a permutation is. I already told you this yesterday before we even started the first lesson. A permutation is an arrangement of items, and the word arrangement means order is important. You know, if I take a flower arranging class, I don't just take the flowers and dump them in my vase and go, ta-da. I mean, you have to arrange them. They go in a certain place relative to each other. So a permutation is an arrangement. Order is important. Example 2. The only reason why example 2 is different than what we could have asked yesterday is it's using the word permutation. So you already know how to do this. How many permutations are there of all of the letters of the word Regina? 6 factorial, right? And I really want to stop, and I write 7. I really want to stop putting 6 blanks here if that's the extent of the question. I mean, I could put 6 blanks and say, how many different letters could the first one be? 6. How many can the second one be? 5. This should be like just knowledge in your head. So if I talk about how many different arrangements of all of the letters of the word Ashmont are there, it would be 7 factorial. And I'm going to go to the handout here because I just realized I didn't change something in my notebook program. Let's read through this together, which is a little bit different than what's in my file. So, what happens if we take fewer number of items to arrange out of a larger number? So what do I mean by that? If I had 7 different cookies, and my mom said, Paul, you can only eat 4 of them. How many ways can I eat 4 cookies? Well, I could have the coconut cookie, followed by the chocolate chip cookie, followed by the macaron, followed by the snickerdoodle. Or I could eat those same 4 cookies in a different order. Or I could not even touch those 4 cookies and instead go for the Florentine cookie, and the oatmeal cookie, and the raisin cookie. I could do that, right? So that's an example of taking fewer items out of the total. And we write it as 7p4. This is what we write the answer as, without knowing the value of the answer. We say there are 7 items and we are permuting 4. I don't know if permuting is a verb or not, but I will often say 7 permute 4. We're permuting 4 of the items. We're arranging them. There are 8 empty seats on a bus and 6 people get on the bus, it should say. I'll have to fix that typo. How many different ways can they be seated? Well, order is important, right? If only one of those 8 seats are a window seat, maybe you want that window seat. Maybe you don't want the window seat. I don't know. But the order of the seating is important, so that would be 8p6. How many 3-letter arrangements can be made using the letters from the words Roxy Music? Well, you have, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 different letters. We're going to arrange 6. Sorry, we're going to arrange 3. And it turns out, and now I'm going to go back to my notes, it turns out that the number of ways of arranging a certain number of items out of a total number of items is n factorial over n minus r factorial. Okay, so for example, how many cookies was it? 7? Okay. 7 cookies, arrange, I was allowed 4. 4. This is equal to 7 factorial over 7 minus 4 factorial, which is 7 factorial over 3 factorial. Would you agree? Okay, let's not worry about what that number is. If you solved this cookie problem using the fundamental counting principle, you would say cookie 1, cookie 2, cookie 3, cookie 4, and you would say that there are 7 cookies that I can choose from to gobble my first one, then there are 6, then there are 5, and then there are 4. How many of you see that 7 factorial over 3 factorial is 7 times 6 times 5 times 4? Because the 3 factorial is contained in the 7 factorial. And this is what I think, Thomas, you and I were talking about yesterday. You figured that out before I even told you this formula. 7 times 6 times 5 times 4 factorial, times 4 times 3 factorial over 3 factorial leaves you with the 7 times 6 times 5 times 4. All right. So, how many different arrangements are there using 4 letters from the word Ashmont? Is this your example 3? Okay. Well, the answer is 7P4. Right? If you use the fundamental counting principle, this is the same as the cookie problem, I think, isn't it? It would be first letter, second letter, third letter, fourth letter. It would be 7 times 6 times 5 times 4. And again, we've done this because it's the same as the cookie problem. I'm just going to expand this out just to make sure it's clear to everybody. This is 3 factorial, and you're left with that. That's using the n factorial over n minus r factorial. The top is 7 factorial. The bottom, this is 7 minus 4 factorial. That's the formula. But we don't have to do that. And I'm sorry, I really should have pointed that out. This is n, this is r, so n factorial over n minus r factorial will be 7 factorial over 7 minus 4 factorial. Okay. But we don't have to do it that way. In fact, I don't know why we would do it that way from here on in. On my calculator, I go 7. I go hunting where I would find factorials, but I discover there's an NPR function. And then I put 4. And I get 840, which will be 7 times 6 times 5 times 4. It better be anyway. If you do that here, I'm not sure what happens here. I don't know if you have that on. Yeah, you don't. I thought maybe on your calculator where the R and the N were that there would be little places you can put the numbers in. Does anybody have a calculator where that happens? Okay. So on the most current TI model, you can actually put the numbers in there. On an 83, I'm assuming an 84 doesn't have that option. Okay. On an 83 or even an 84, it doesn't have that option. So you wouldn't worry about it. You would just enter it. It looks clunky. It looks wrong. I mean, that doesn't look right. That's not how we write it. But that's what it is. Okay. Why is 0 factorial 0? Or why is 0 factorial 1? If I said to you, how many ways are there to arrange n items all at a time? We know that's n factorial, don't we? How many ways to arrange 7 books on a shelf if we have 7 books to choose from? 7 factorial. But if we apply, I'll use an example. If we apply the 2 7s to this formula, then you're going to get 7p7 equals 7 factorial over 7 minus 7 factorial. You're going to get 7 factorial over 0 factorial, right? But you know the answer is 7 factorial. The only way that can make sense is if we just make a blanket decision that says 0 factorial is 1. We need to know that. Okay. All right, a couple more questions we're going to do here. In a particular country, license plates consist of 2 different letters followed by 4 different digits. How many plates are there? Well, if you use the fundamental counting principle, this is what you would do. And I want everybody to just roll that around upstairs for a minute and see if that makes sense to you. Yep.
Do we always have to apply the rule where you can't use ones and zeros and i's and whatever?
No, but in this case, that rule? No, no. Only if you're told.
Okay.
Yeah. You're talking about no I's and no O's.
Yes,
Yeah,
just
no.
for license.
No. Thought you were going to ask something different. I apologize. And by the way, these numbers are diminishing each time because we have different letters and different numbers. You can't use the same one. I'm not worried about what that works out to. If you have a minute, you can figure it out. But the bottom line is this. Instead of putting on a pair of pants and a shirt, you have to choose 2 letters and arrange them out of 26. And you need to arrange out of 10 digits 4 of them. That's the answer. And that might even be the answer on a multiple choice. It might say A, 26P2 times 10P4. I really wish that TI would have designed their calculators so that the NPR and the factorial and all this stuff was right on the front. Yeah, it would just make things so much easier. On the newest of calculators, it is still buried in the math menu.
It goes into the formula, like it says 7P4.
It actually shows it, yeah. But I wish the button itself and accessing it were in a better place. Anyway, you would have to go 26 P2 times 10. You'll get used to this and it will get faster. And it looks horrible. It really does not look like what it's meant to look like. But I want to make sure that you understand that this NPR locks this together. It's not going to multiply 2 by 10. Okay, it won't do that. So you don't need brackets. Anyway, the answer is 3,276,000. Okay, let's move on. Solve this equation. What? Is yours different?
Yes.
Okay.
It is NP3.
This one?
Yes.
Okay. Solve this equation. Okay. Well, how are we going to solve this equation? I guess the only thing we can do is apply our NPR formula to this, NP3. And we would get, since NPR is n factorial over n minus r factorial, this is going to be n factorial over n minus 3 factorial equals to 2n times n plus 8. Now, how can we simplify that? Well, n minus 3 factorial has to be contained in n factorial. And we expand out the n factorial until we see the n minus 3 factorial. So I could keep going. N factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4. But the n minus 3 to the end of the line is n minus 3 factorial. And I'm stopping there so that I can do this. And this is equal to 2n times n plus 8. And right away, I want to rewrite this just so you can see it. Right away, you have changed this from a Unit 7 Math 30 problem to a polynomial equation Math 30 problem. But we can also do this. And now what you have changed it to is a quadratic equation Math 20 problem. I can FOIL out the left-hand side. I can expand out the right-hand side. And now it's getting, well, it's getting a lot simpler. And that's, you know that. That's my philosophy. You do stuff to equations to make them simpler equations. I can subtract 2n from both sides and get n squared minus 5n, and I subtract 16 from both sides and get minus 14 equals 0. I have a question for you. Why must this be factorable? Isaac?
Because we have to have a whole number as the factorial.
Right. We have to have a whole number here for n. Looking at this original statement, though, can you tell me anything else? Looking here, can you tell me anything else that has to be true about n?
It can't be smaller than 3.
Can't be smaller than 3. So we'll talk about that in detail, but from a practical standpoint, in a second, from a practical standpoint, you can't have 2 arranged 3. You can have 3 arranged 3. You can have 4 arranged 3. So it must be a whole number greater than or equal to 3. And since it has to be a whole number, you wouldn't be asked to solve this unless it were factorable, because things that are not factorable don't give us rational answers. They give us irrational numbers. What 2 numbers multiply to give negative 14 and add to give negative 5? I believe that's 2 and negative 7. Which means n is equal to negative 2, and n is equal to positive 7, and of course, negative 2 is kicked over the boards. So the answer is 7. Now you could certainly, if this is not a written response question, and sometimes it isn't, but sometimes you see these as multiple choice numerical response questions, you can do the following. X in for y1, p3, and then for y2, 2x, x minus 8, plus 8. Don't attempt to solve this graphically because there will be no graph for xpr. Your calculator just jitters around, it doesn't know what to do. Okay? But we can go to our table. We can set up our table to start at 3 because we know that it has to be at least 3 and go up by 1. And we go to the table. We're looking for where these numbers are equal. Oh, right there. Both sides are equal to 210 at 7. I was very strategic in saying starting at 3 because if you do scroll up to 2p3 does have a value. And that's why I said in answer to your question, practically speaking, that's right. N must be greater than or equal to 3. And we're dealing in this unit with practicality. Why is 2p3 equal to 0? Because there are no ways to arrange 3 items out of a group of 2.